Welcome to our talk on Undefined Behavior. Thank you so much for being here. We really appreciate your coming to our talk. And you have the clicker. Thank you. So what we have here is we're going to break down our talk today into several different categories. One of the key things we want to make sure we address with undefined behavior is the definitions, because some of the definitions of undefined behavior have changed in newer versions of C++. So this is just kind of an overview of what we're going to talk about today. So why are we doing this talk, and who are we? Because I'm sure there's some of you who don't know who we are. Obviously that's Ansel, and I'm Barbara. But who we are is the co-founders and the maintainers of the CopperSpice project. CopperSpice is a set of cross-platform GUI libraries. And in addition to CopperSpice, we also develop DoxyPress, which is a documenting program, and we tend to favor mostly for C++, although it can do several languages. The other three libraries that you see below that, these are libraries we have developed that you can use in any C++ application. And we also use them internally, because what we're trying to do with CopperSpice is take it away from a framework and turn it into a set of libraries. Everything we do is open source, everything is free, most everything is BSD, a few things are LGPL, and our idea is to contribute to modern C++. About a year ago, we started a YouTube channel. Most of the videos are about C++. A few of them are about our projects. But what we really found was being a library developer, undefined behavior became a really critical topic. Because as a library developer, we can't afford to have undefined behavior at all, because it will affect every application you're developing.
So one of the things we wanted to first address in this talk is, first of all, why are we giving this talk? And part of the reason is there are many, many topics that have been brought up, and many people have done sessions on what undefined behavior looks like from the compiler's point of view, or from the perspective of somebody writing an optimizer. And they're fascinating, and I love watching them. But at the end of the talk, usually I find myself saying, is this actually going to change the way I write code? Did I learn something that I can change in my application or library development area so that I can improve my software? Is it worth studying compilers to understand how undefined behavior works? Not necessarily, because looking at it through that lens may not teach you enough about what to actually avoid. So we wanted to give a talk that was accessible to a different set of programmers who may not be as used to thinking about these terms. And the first place that we wanted to start is, what do typical C++ programmers, what do they come from when they're looking at undefined behavior? Well, a lot of them believe that compilers should report undefined behavior as an error. And some is, but unfortunately in the general case, this is not true. There's a very common belief that if you're an experienced developer, you'll easily be able to avoid undefined behavior in your code. Or that it's not really your responsibility. Maybe you might think that it's part of the QA process and the testing of your software that should find and eliminate undefined behavior. And there's also a persistent belief that undefined behavior is something you can see in your code and you can debug once it has happened. And this is really just not the way it works. So what we really need to study about undefined behavior is to start with the idea of, what do I actually need to learn to understand what it is? Can you avoid it? If so, how? And how do you debug it once it has occurred?
So we need to go over some terminology. And we threw this slide together because we found it of value that there are words that have been confiscated by C++, like semantics. The idea that we can say there's a brave lawnmower, that's grammatically correct in English, but it has no semantical meaning. And the word semantics in C++ has a completely different meaning. So that's why we wanted to start to show this, that we have to be careful with our language and careful how we define things.
It's also very common for people to talk about maybe a parameter that has a default value as optional. Well, unfortunately, the word optional is now used by the standard to mean a very specific thing. It's a new data type that may or may not contain a value. If you say that parameter is optional, I may not know what you mean.
These are other terms which are going to be confiscated and used and have specific meanings. And if you're doing teaching or you're studying the language, you're going to need to start to remove some of these words from just your normal vocabulary. Because as C++20 comes out, all of these terms are going to start to be used. And spaceship, although it's silly and it's funny, if you're on a project that is a military project, you might actually have a class called shuttle. And you're going to have to watch how your language is. The reason why we're bringing this up is the same thing happens with undefined behavior. These are terms which have specific meanings. And these is terminology that unless you understand exactly what they mean, you're not going to actually be talking about undefined behavior. So that's why we wanted to bring the terminology together.
So let's talk a little bit about the precise terminology that the standard uses to describe how your program behaves. And these are definitions that are paraphrased somewhat from the standard, although the essence is present, because the standard definitions are longer and less clear. Defined behavior is pretty simple. It's most of the code that you write. It's code that has a single, unambiguous, well-defined meaning prescribed by the standard. If you execute this first declaration, and there isn't at the end of the declaration a variable called sum in your program with the value 7, your compiler is broken. It has violated the standard. Similarly, we all know what a printf does. It's supposed to print a string to the standard output. These have a single, very well-defined meaning. Slightly less well-defined is the idea of implementation-defined behavior. And this is code which can be interpreted in multiple different ways depending upon the compiler and the platform. However, it has to have one of those possible meanings that the standard prescribes, and the compiler has to pick one and document that choice. So here's a typical example. I'm testing to see if the size of int is less than the size of long. And the standard doesn't say whether this is true or false, but it must be either true or false, and it must always be consistently true or false on a given compiler and platform. And then slightly less defined than that, there's the term of unspecified behavior, where again we have multiple possible meanings, but the standard doesn't require any sort of consistent choice by the compiler. One of the things which is unspecified is whether or not two string literals that have the same contents reside at the same address. The compiler is allowed to fold these together into one constant so they have the same address, which is what we're testing here. This if statement may be either taken or not taken randomly according to whatever the compiler happened to do on that compilation or even a particular execution of your program. But it must be either taken or not taken. It can only use one of those two possible meanings for your code.
Whereas undefined behavior, the basic definition is the code has no meaning. Absolutely. So if you have undefined behavior, the code has no meaning. This is the most simplistic form of the definition. Most of us are aware of dereferencing a null pointer. That's wrong. That has no meaning. That is something you can't do. So this is just a very, very small subset of the things which have no meaning, and they must be avoided.
There's another section which the standard really doesn't touch on, and the reason is it's not relevant. But it's very important to us as programmers because we distinguish a lot of the times between an error and successful completion of the program, the intended behavior, what we wanted it to do. It's important to understand that from the standpoint of the standard, these are not distinguishable concepts. It's just your program is following some sequence of meaningful operations and produces a result. Some of those meaningful operations may be errors. You may have a file not found or get an out-of-memory error, or the socket wasn't available. Quite often you might have an assertion in your code saying this value can't be negative at this place in my calculation, or you might be throwing an exception, or you might get an exception from calling a standard library method. But there's no difference between that and a correctly running program from the standards viewpoint. These are all defined behavior.
So they are not undefined, and that's why we wanted to be specific on the difference between these terms. So what is undefined behavior? It is the result of attempting to execute source code whose behavior is not defined by the standard. That's a more concise definition. We're still sticking with the definition that it has no meaning. But the standard clearly says, if you do this, it isn't defined. You can't. And this sounds very restrictive. It's intended for that. And it is your responsibility as a programmer not to have undefined behavior. It is not the responsibility of the compiler or of any type of analysis program to say, maybe you shouldn't do that. The truth is, it is your responsibility to not write that type of code.
And a correct program has to be entirely free of undefined behavior. Or to say that a different way, if your program has undefined behavior, your program is not correct and does not meet any specification. Because if you execute an operation that has undefined behavior, it's retroactive. The compiler can retroactively decide that your entire program has undefined behavior and cause strange results. The standard makes no guarantee of your entire program's function at runtime.
So let's take a look at a silly example. I have a recipe for chocolate cake, and it's the rules that define a chocolate cake. And the recipe says, if you make this chocolate cake, it's going to be a wonderful chocolate cake, and it's going to be that chocolate cake. I happen to know my recipe says you can use walnuts. It's optional. I personally don't like walnuts, so I leave it out. That is implementation defined. But the recipe also says there's 1 teaspoon of salt. And if you decide you love salt and you add a cup of salt, first of all, I can tell you it's a terrible cake. You will not enjoy eating this chocolate cake. But more than anything, you have undefined behavior. But it's not just the salt, it's the entire cake is undefined behavior.
Now, the thing about undefined behavior is anything could happen. If you have a recipe that calls for milk and you use soy milk, you're also in undefined behavior because you're not following what the recipe called for. But it might work. It might produce something pretty close to what the original intent was of the recipe. But you're still in undefined behavior. You can't make any guarantees based on the recipe about the result you will have when it comes out of the oven.
So why are we studying undefined behavior? Well, because it's complicated, and it's subtle, and it bites us, and we need to be aware. And there are crashes we sometimes see in programs. People say, well, it's a minor crash. It doesn't happen all the time. But again, if that crash is happening because of undefined behavior, then your whole program is undefined, and you have to take it seriously.
And people tolerate undefined behavior because oftentimes the code seems to work in production, and so there are other things that are higher priorities. It's very important to push back on this idea, and particularly if you're writing any sort of application that uses untrusted user input, any sort of network connection, or anything that could read data from a malicious user. Because undefined behavior gives an area for a malicious user to feed data into your program you didn't expect and cause it to do things that you didn't write the code for. And of course, the canonical example of this is the old joke of a parent who names their child Robert, quote, semicolon, drop table students. And when they enroll for the first day of classes, hilarity ensues and the school loses their entire database. This is something you should avoid, and you should make sure to sanitize all of the inputs so that you can't have undefined behavior in that way.
So here's a case study we wanted to take a look at. In one of the things that we were working on, we needed to design a metadata registration system to implement runtime reflection. We did it. And this was several years ago, and it was incredible, and it was awesome. And then we decided, why don't we ask some compiler people? And we did. And it was humiliating. We were leveraging undefined behavior. But it wasn't caught by the compiler. And what we were told is, it will in about 6 months. You're on the edge of undefined behavior, and thank you for showing us your code. They said, go do it again. And we were stuck for a while. We said, now what? We did registration 2, and that was just, it never saw the light of day. What we were doing to do reflection on this version 3 is our compile time counter. We've also done some videos and some presentations on it. And yes, it uses method overloading and const expr and a recursive template with a non-type template parameter. And it's intense code, but it doesn't have undefined behavior. We did take it back to some compiler people. We did have them bless it as much as they could. That's how insidious undefined behavior is the feeling that we had done such a great job on version 1, and we didn't.
So here's a partial list of the things which the standard explicitly says are undefined behavior. You must not do any of these things, or your program has undefined behavior. And a lot of these are common knowledge. I mean, most accomplished C++ programmers know you shouldn't dereference a null pointer, although they may think of it as an error. They may think of it as, oh, that causes a seg fault. Well, that's not actually true. It's just undefined behavior. You can't reason about what it will do. But some of these are a little surprising, like having an infinite loop without side effects is undefined behavior. The compiler is allowed to do whatever it wants with your code. Or an integer divide by 0. You can't trap that because it's undefined behavior. Signed integer overflow is the source of many issues in numeric code because it's undefined behavior.
So this was the fun part to us. We were really looking at the idea of what is undefined behavior. It's not an error. So we coined the term ubine, that undefined behavior is not an error. It's undefined. And I know we're kind of harping on that, but it's that important because at times people are saying, well, that's okay, I can have some undefined behavior, it'll just cause an error or I'll check it. You can't. You can't really run this and verify. You just have to not do it.
That's a very fundamental point and it bears repeating. You cannot handle undefined behavior. Once it has occurred, there is nothing you can do to recover from it because the entire state of your program is undefined and no code executing after it has any meaning whatsoever, according to the standard. Now, errors, on the other hand, are well defined. We've all done plenty of compile errors, missing semicolons, function calls that don't match, things like that.
Missing include files.
Missing include files, I've done that a few times. There's certainly lots of code that results in a runtime error. Note that a floating point divide by 0 is a runtime error, not undefined behavior, so you can handle it in certain ways. Things like if you're using the threading library, destroying a thread without joining or detaching it. That's a runtime error. You can handle it in some way. Or calling at. If your vector doesn't have enough elements, you get an exception. It's well-defined behavior. It's just probably not the behavior you wanted.
So we have another thing that we came up with was the compiler of the future, the EC compiler. And I happen to think compilers of the future are going to be really efficient and they're going to really remove my undefined behavior and they're going to optimize it.
And I look at the compilers of the future as more evil. They're going to find ways to twist the meaning of my code that I wrote if they can find undefined behavior in it. So I want to program very defensively and make sure that I can state unequivocally that every line of my program is defined and has a meaning. Because it could do something really unexpected if you have undefined behavior.
Oh, I don't want the undefined behavior, but I'm really glad that compilers are efficient because I want it to remove that code. And that's what makes me happy, is efficient compilers.
And the truth is there's really no difference between efficiency and evilness here, because the aim of the compiler is to make your code run faster, taking advantage of the fact that it knows you have no undefined behavior. One of the things to note about compilers is that if you have optimization turned off, most of them do a pretty literal translation of your code. So a lot of things that are undefined behavior will behave the way you expect them to, because they got translated literally. But if you turn optimization on and your code breaks, it's very likely you have undefined behavior because all of a sudden the compiler is looking more into the intent and the meaning of your code, and it discovered that it didn't have any. So it threw it out or did something unusual.
So here's an example that, of course, we did one time. We left off the return. And the reason why this is a value returning function is because of the bool. The best thing that can happen is it crashes, which ours didn't. The worst thing would probably be that it just always returns true. What actually happened to us was the last one, that it just went to the next function in the executable and just randomly started executing the next set of code. This is a fairly simple example, and with the right warnings, compilers can detect this. But if your code is more complicated, it may not see it, and you may have a missing return. And you just have to not do that. And I know that's not fair, but you have to put the return in.
Here's an example in some code that we inherited and had to debug. Well, accessing an element of a container using operator brackets that is out of bounds is undefined behavior. Standard explicitly says that. And the operator bracket in this case returns a reference to an element in the string, and it has to be a valid element to work properly. There's no test in this code to make sure that the indices that we're using are valid. So what actually happened in this code is the compiler looked at it and said, you're indexing two elements off the end, or off of whatever position in the string you're currently looking at. Which means if this loop ever reaches its last iteration, it's undefined behavior. Which means the only way for this code not to be undefined behavior is if the loop body never executes. Therefore, the input string is always empty. So the output string will always be empty.
And class name was always empty. And it baffled us until we realized it was undefined behavior.
So this code was just removed by the compiler.
Optimized away in my efficient compiler. Okay. So here was another example. We were debugging some code we had written, and we were using a printf. We had a crash. And in our printf, we were using a QString. And if you're not familiar with the QString, it's the equivalent of an STD string for the purpose of looking at this. But the crash kept moving as we moved the printf. It was moving all over the place. So we decided to put some more messages, and we use a const character star, and the bug went away. So we put the printf back with the QString and back and forth until we said, maybe it's not our code, maybe it's the actual QString that's broken.
This turned out to be the case because QString had a static data member, and as we saw on a previous slide, using an uninitialized variable is one of the things that is defined as undefined behavior, and it's not specified which order static data members get created in, get initialized. So we ended up using that data member before it was initialized, and we had all manner of strange crashes. So we had to wrap that static data member inside a function, make it a function local static, which was guaranteed to be initialized on first use, and then all of our problems went away in this case. This is one that caught us because we were trying to explain the idea of undefined behavior, and we thought this was. But you have to read the standard very carefully when you're trying to determine what's well defined. So the standard says relational comparison of pointers is only defined if the pointers point to members of the same object or elements of the same array. Well, these are two locals. They're not part of the same object. They're not part of the same array. And it's clear from reading the standard that if you compare these for equality, that test is false because they're definitely not at the same address. But it seemed like it was undefined behavior. There's a separate rule elsewhere in the standard that says all relational comparisons of pointers that are not defined are unspecified. So that means this has to return either true or false. It's not undefined behavior. But it was very hard to determine that from reading the standard. And as a result of this, there's actually a defect report filed on the standard, and there's going to be an editorial change in the next version, most likely, to clarify the wording.
Yay.
This is a function that computes the sum of the first n numbers. And just by looking at some of the arithmetic, you can see if max is a very large number, and it easily can be, the result will overflow. and signed integer overflow is undefined behavior. Well, since signed integer overflow is undefined behavior, the compiler can actually remove the for loop, because there's a way to compute this number, Gauss's theorem, that was determined many years ago, and Clang knows this trick, and it will remove the for loop completely and replace this with a multiply and a divide. However, that version doesn't give you the same answer that this for loop would if the integer overflows, but that doesn't matter, because integer overflow is not allowed, signed integer overflow. So it's your responsibility to never call this function with a value that's too large.
Constcast is something that is obviously used to remove the constness. And in this example, we are not talking about the fact that the parameter received by this function is const. What can make this undefined is if the original value was const. So if the original value was const, and then you do this constcast, you have undefined behavior. So this is something that isn't always undefined, only if the original value was const, and then you do the constcast. This can become an issue in multi-threading as well, and you have to be careful if you're going to do a constcast, how was it originally declared?
This function and the one preceding it are particular cases of a general thing that you need to be aware of. There are many functions we write that are undefined behavior for certain inputs, but not others, and you need to be very careful of that in your code.
Okay. Quickly.
Here's another one that many people are not aware of in the standard. It says specializing a standard type trait is undefined behavior. And most compilers will accept this code without any warning or complaint, and at the end of the slide, you'll get the result in test that says int is a pointer. This is clearly nonsense, and it'll break all the standard algorithms in strange ways, so it's just marked as undefined behavior. You can define your own type traits, that's fine, but don't ever specialize a type trait that's defined by the standard, because you will get bizarre behavior.
So now as we start switching, we want to talk about sequencing. And sequencing has to do with a location in your code, usually at the place where you're finding your semicolon, where the side effects from all previous expressions are complete, and pending expressions beyond that location have not been evaluated. So sequencing is a really important topic, and a sequence point is really a place, a location, that everything is kind of before has happened, things haven't started. This is sort of how optimizers work, is they're looking for that place where they can call, we have this point, and everything is resolved at that point.
Now, this is a really important thing to be aware of because we as programmers write code in order, and we reason about the code in order. But it's only the existence of sequencing that forces the compiler to actually do what we told it to do in the order we told it to do. And sequence points have been there since the beginning of C++. Now, the definition of sequence point includes the idea of a side effect. And so in order to understand this, you really need to understand what a side effect is. And the standard says, an expression has a side effect if it modifies some state in your program or does anything beyond returning a value. The side effects that exist are reading a volatile object, write access to any object, calling a library function to do I/O, or calling some other function that does any of these things.
So now we've reached the audience participation time. We have line 1, line 2. We're going to ask how many side effects on line 1? 0. Hands? Anybody with 0 side effects on line 1? 1 side effect? 2? 3? Why is there 1 side effect on this?
The reason is that this expression, var a equals 5, evaluates to 5. That's its purpose. The side effect is assigning the value 5 to var a. How many side effects on the second line? 1, 2, 3.
We have some 3s. Tentative hands are saying 2. 2 side effects.
There are 2 side effects here. One, Question?
If var A was volatile, it would be a different result.
That's true.
That is true.
We'd have 3 side effects then. That's true. I assumed this was not volatile. That was.
We assume that.
So there are 2 side effects on this line, assuming nothing is volatile, because we have the decrement of var A and the assignment to var B. So we have 2 side effects.
So in all reality, sequence points ended with C++11. Sequence points were dropped out of the standard. Sequencing is the new definition, and it is involving sequence before and sequence after. And they changed this because if there is just a sequence point, and we're looking at the end of, it can be a comma or a semicolon a couple places, but the point is locations were more limited. By sequence before and sequence after, now compilers could get a little more creative. It may span 2 expressions. Maybe not, but it could. And this is the idea, is where is the sequence before and the sequence after? So the idea with C++11 is to start giving compiler designers more freedom of how they can optimize.
Now, if you have 2 expressions and they're not sequenced before or after each other, there's 2 possibilities. They could be indeterminately sequenced, which means one happens first, but you don't know which one. Or they could be unsequenced, which means neither of them happens first and their execution could be interleaved in your program. And this turns out to have some consequences, as we'll see.
So let's take a look at this example. 2 side effects, and this is a quote from both 11 and 17. If 2 side effects or a side effect and a read occur on the same object, they are unsequenced. And you have undefined behavior. So we're looking at these 2 examples, and we're asking, are these defined or undefined behavior?
Who's for defined on the first one? Who's for undefined?
Looks like about even.
What about the second one?
one?
Defined?
Defined.
Undefined. Okay.
Okay.
Well, unfortunately, we're all wrong because it depends on the standard.
If it was 03, it's always undefined. In 11, things changed as we moved from location, talking now about sequence before and sequence after. And the real rule that started to apply then in 11 is we've got the left operand and the right operand. And in 11, the idea is one of them is going to happen, but we don't know which. But they're both going to happen before the assignment.
And that makes the first expression valid and legal and guaranteed to result in var A being set to 8.
In the second example, it's not defined until 17. And what happened in 17 is it's guaranteeing the right operand is evaluated before the left operand, before the assignment. And it changed. And this is not something we believe that everybody has become aware about. Certainly we were caught off guard with the idea that things can be defined in 11 and they were undefined until 17. Was there a question or? No? Okay.
Another thing which is interesting is the order in which function parameters are evaluated. And originally, function parameter evaluation was unspecified. You could interleave the evaluation of the different functions. As of C++17, the order has been upgraded to indeterminate. And you're always guaranteed that the arguments are evaluated before the function call. This makes sense because you need the arguments in order to start executing the function. So here's an example where we have a function call and the expressions that are being passed as arguments have side effects. So it matters which order they occur in. Does anybody know which is, whether this is defined or undefined? Very good answer. It's undefined because the sequence is not known. The compiler could choose the first sequence, It could assign to var1 first by calling doThing1, and then pass var1 to doThing2. And if the compiler chooses that option, as it can, then this code has a meaning. If the compiler chooses the other option, this code is meaningless, because we're using a variable before it's been initialized. So this is a case where something which is indeterminate can end up causing undefined behavior if the order in which the operations occur matters.
I think we're basically advocating don't write code like this, because you don't know what the compiler is going to do. I don't know if we had actually said that. We're not advocating some of these mistakes. We're saying this is what to look for in your code.
Be very cautious of code that has side effects in places where you don't know what order the expressions will be evaluated in.
Okay, quiz time again. So here's some code. I will tell you one of these is the right answer. It's probably not boot sector, but it could be.
If it's undefined behavior, that could happen.
Anybody want to comment? Anybody want to be brave?
Which version of the standard?
Which version? Oh, that's a good question.
Good
Which
question.
version of the standard? You get to pick. That is an excellent question. We tried to make the math very simple so fingers would work. So we're obviously looking at a post increment. We're adding 3. We're saving it back to an array, but to which element? Do we have some guesses? So we were just going to do 1, 2, 3, 4, 5. So the second one, we have a vote for the second one. The second one.
Well, again, it depends on which version of the standard. Because in C++11, this is still undefined. And the reason why is a little tricky. The rule about order of evaluation of operands says the value computations, but not the side effects, of the operands to any operator are sequenced before the value computation of the result of the operator, but not its side effects. So these expressions have to be evaluated in a particular order, but their side effects are not ordered. And
again,
since we have 2 side effects operating on the same variable, it's undefined.
So again, we don't know which side is going to get done. We know both the left and right operand are done before the assignment, but we don't know which. So yes, this is undefined in 11.
When we get to 17, applying some of the rules we talked about previously and this one, which was added in 17, it becomes defined behavior. And this rule says that in the subscript expression that we have on the left side of the assignment, every value computation and side effect of the inner part, it happens before every value computation and side effect of the outer part. And that's enough to give this defined behavior. And you can work through the math and realize that the right side is evaluated before the left in sequence, and you'll discover that we're assigning the value 7 to the 5th element of the array, and at the end of it, var b will be 6. Now, there's a little issue with working on code like this.
And that's the problem, that the compilers are still reporting errors. They're reporting a warning. They will compile this. It does work. We tested various versions of GCC and Clang. We also tested a nightly build on Sunday. These warnings still come up in Clang and GCC.
Now you note that GCC's warning is not technically incorrect because it says the operation may be undefined. So they're hedging their bets there. Clang just says you have an unsequenced modification on this variable, and it's incorrect.
So at least now if you see this error, you might start looking at your undefined behavior. But the problem is if you're in 17, it may not be undefined behavior. So now we have my efficient evil compiler that is giving me a warning when it may not be. So now we're at a place of saying, don't ignore warnings unless they're not right, Mr. Evil Compiler.
So this is a poor place to be in, and we went looking to find out why are we still in this situation in C++17. And while we don't have documentation on this for Clang, the GCC team did document their rationale. Because there are many examples that you can find that are shown to be defined in C++17 and undefined previously. You can find these on CPP reference fairly easily.
Yes, the CPP reference under the evaluation order was a page we looked at quite a bit, and there's several different examples. But GCC is absolutely claiming, yes, it's a warning, yes, we know it's defined, but just in case somebody on your team is using an older compiler, why don't we throw a warning up anyway? I don't know if that's right. So it's going to be up to you to decide how many different compilers you're using and what versions, and are you fully on 17? Or are you on 14 or 11?
Now, I will state without proof that code like this that tickles the edges of undefined behavior and is only barely defined in C++17 is probably not code you should be using. So if you get one of these warnings, it's probably a sign to redesign your code so that you're not in this area. But you may have a use case for it, in which case you'll need to become very familiar with these sections of the standard.
So one of the other things we wanted to make sure that fit in the technology of all this is undocumented behavior. There's no flat map currently in the standard library. We needed a flat map in our CopperSpice library, so we created a Q flat map. And a flat map, if you're not familiar with it, it sort of looks like an STD vector in terms of memory, and it uses the API of an STD map. But since there is no flat map, we did ask ourselves, is this undefined? No, it is undocumented behavior. So we wrote a flat map, and we added it to our stuff. It'll probably eventually be in the standard library, and you could have written this for your own project. But one of the things we wanted to mention was make sure the abstraction and the implementation fits the model of what you see existing in the standard library, and don't add undefined behavior. So make sure what you're doing is defined behavior. But the idea is this is how you extend. And you probably do it all the time. By your classes and what you're implementing, you're extending the language. And that's what we are categorizing as undocumented behavior.
So I'm going to contrast this with the idea that doing something the standard doesn't explicitly specify is undefined behavior. Because the standard says anything which is not explicitly defined in the standard is undefined behavior. But when we add new classes, as we all do, or add new functionality, write functions, we're using behavior defined by the standard to extend the language. That means it has a well-defined meaning. This is not what we're talking about when we say undefined behavior. And it may seem like a trivial point, but I found that often people get stuck on this point of, well, I'm using something that's not in the standard. It must be undefined behavior, and that's simply not the case.
So now the interesting question is, how do you avoid all this? That's what we ultimately want to do. You can't just go around and memorize every single piece of undefined behavior. You can come close, but you have to get proficient at understanding sequencing and understanding what might be undefined behavior. So part of this is writing accurate code, writing correct code, and paying attention to the compiler warnings unless they're warning you in 17, which we're not sure the answer of that one. But you have to read the standard. And I do find reading the standard awkward. Ansel finds it quite enjoyable. But I consult CPP reference a lot. It is the best place if you're not going to read everything in the standard because the language is a little bit obscure. CPP reference is extremely accurate, and it's worth looking at. And it has great examples.
There are a couple of things you should do proactively to prevent undefined behavior in your code. And two of them are kind of similar. You should try your code with a large set of compilers, different versions, all the warnings turned on, and you should do regular code reviews for much the same reason. The more eyes and the more compilers are on your code, the more likely somebody is to say, are you sure that's a meaningful operation? Does that make sense? Does that have a well-defined meaning in the standard? You also need to test crazy corner cases because, as we've showed, there are many, many functions, very common in pretty much every program, that have undefined behavior for certain inputs. And it's important to make sure that either they trap those inputs before the undefined behavior occurs, or you make sure that none of the call sites ever could pass those inputs into the functions.
We also advocate testing these crazy corner cases, even if you know they would never happen in your code. Test them anyway. Test the things that can never happen because they might.
It's also very important to treat undefined behavior as a critical bug, because if you have one place in your program that has undefined behavior, you cannot reason about the proper operation of your entire program. So it is, by definition, the most critical bug you can have, because it makes your entire program a bug, and you have no idea where it may show up. Now, there are certainly tools that we can use to help find some of the cases of undefined behavior. There are some static analysis tools. Coverity is quite good. The Clang static analyzer can find a lot of undefined behavior at compile time. And there's a tool called Purify that does a great job of this as well. There's also a growing group of sanitizers that instrument your code and at runtime will check to make sure that everything you're about to do has a meaning and is well defined according to the standard. Now, these can't find all undefined behavior. They can only find the undefined behavior they've been designed to catch. But since these cover the majority of typical undefined behavior that you'll do in your code, it's quite helpful to use them. These exist on both Clang and GCC. The Clang suite is a little wider, but they both do a pretty good job. And then there's also Valgrind, which is a very useful third-party tool that I've used for years, and it's great if you don't have the opportunity easily to recompile a particular piece of code, because since it's not part of the compiler, it can be run directly on an existing executable.
One of the things to mention about trying to test is a lot of us have grown accustomed to using Godbolt. And if you're not familiar with godbolt.org, you should be, because it's a great place to go test your code, various compilers, and various versions of everything. But the problem is, although we tested our code, we were testing code that we knew had undefined behavior. So sometimes Godbolt would say, yes, it's undefined. Other times it didn't. So this gets back to, well, how do I test undefined behavior? You have to read the code. You have to look at it. You have to be aware of what causes undefined behavior, which is why we felt like stressing the sequencing idea and stressing corner cases really brought it together in the idea that this is something you have to get proficient at and you can't ignore. So in just wrapping up, we wanted to mention that yes, we do have our YouTube channel. This is a list of some of our current videos. Our const expert static const was a recent video we did, which was quite exciting. We hope that you subscribe to our channel, a YouTube CopperSpice. Most of these are about C++, and we did do a video a while back on undefined behavior, but it was a much smaller subset of what we've talked about today. We have a lot of interesting talks coming up. One of ours coming up later this year will be about what to do if your code base is old enough to vote. So that's one of the topics coming up, and various other things. If there's something you want to see us do a presentation on, we're very happy to do that. And go to the next slide. And just to recap, this CopperSpice is our main project with our other libraries. And again, if you're a C++ programmer and you need a string library, we have this. You don't need to be using CopperSpice. One of the other projects that we have done is Kitchen Sink is a demo program. So if you're not familiar with CopperSpice, Kitchen Sink is intended to show you what CopperSpice can do. And Diamond is an editor that we've done. DoxyPress is a documenting program, and it uses CopperSpice. And it is designed to document C++ code. We use Clang or Lex parsing. If you want it to run faster, you can use the Lex parsing. If you want it accurate, you can use Clang for parsing, and that will produce some fabulous documentation for you. The one other thing we wanted to mention is that if you're looking for an open source project to get involved with. We're really interested in having other people join us and help us remove the undefined behavior and bring everything that we're working on to modern C++. This is some contact information about our website. All of our work is open source. All of it is on GitHub. All of it's available. And that's what we want to do, is share C++. So if there's any questions about undefined behavior, or if we just said everything. Yes? Oh, there's a microphone back there.
Oh, yes, that's right.
You said two things. First, there are absolutely no guarantees about programs' behavior after undefined behavior. And another thing, that everything should be defined. So the question is, what is program in this context? Well, technically, is it executable or one of processes started in the context of executable, or what is program?
I'm thinking about the context of your question. If I understand what you're asking, you're wondering if there's undefined behavior, do you still have a program, or do you still?
Well, for example, I would expect even after undefined behavior that operating system will not crash, and actually behavior of operating system will be defined even after defined behavior. What is the limit? Well, when?
Okay, so the question was about if there's undefined behavior in a program, does your operating system crash, or what's defined to happen in that case? And I'm not an expert on the standard, but my assumption would be that's outside of the scope of what the standard states. So that would be whatever guarantees your operating system makes. And certainly there are environments where there isn't an operating system, but you're using C++. And if you experience undefined behavior, anything could happen. Or if you're in an operating system that doesn't have memory protection between processes, anything could happen.
So do you think that, for example, having multiple processes inside of a single program is a way to catch undefined behavior in one of the processes?
That can sometimes,
that could sometimes
depending upon the behavior that your operating system has, that may be useful. Yeah.
Yes?
So how should we avoid, if possible, undefined behavior that should not be undefined behavior? By which I'm specifically referring to things such as, like, there's work being done to introduce, have you heard of std bless?
Yes.
So there's no standard compliant implementation possible for a container like std vector, because we cannot satisfy both. We are constructing objects one by one in an array, and we also want to allow you to iterate through them using a pointer. So how do we deal with that sort of undefined behavior?
You can't test for it, you can't have it, and where the standard says that's undefined, you can't do it. So although they're looking at adding some of these things in 20, by the time it gets into the standard and it's voted in, it will be said, this is what is undefined, you can't do it. So it isn't a matter of avoiding undefined behavior. That's actually not possible in the sense that you can't have it in your program because the compiler can make pizza. I mean, that is the canonical example, and it's back to the chocolate cake example we gave. If it's too much salt, it's undefined. You can't say, well, I want a little bit more undefined or a little bit less.
My point then is, isn't everyone's program that uses std vector messed up chocolate cake then? Because std vector itself cannot be implemented without this current undefined behavior in the standard?
It's a good question.
It is a good question.
No, go ahead.
I think the most cogent answer I could think of to that is the standard library doesn't have to play by the same rules that user code does. So the standard library can take advantage of knowledge of the implementation that you as a C++ programmer can't. And there are often cases where the standard library makes decisions that a general purpose portable program won't in a certain place. And so it may well be that the standard library implementation of std vector is doing things which are technically undefined behavior, but since it's a close relationship with the compiler, they can define things which would normally be undefined by the standard. That's all I can think of that they are able to get away with that.
This is part of what we ran into with our implementation, which absolutely isn't undefined behavior now, of our compile time counter to simulate reflection. If we could have had access to some of the internals, it would have been a lot easier. And I understand they're working on various aspects of the language to add that, but they need to do it and expose these things so it's not undefined behavior. And there is a balance of that. I hope that helps to explain. Yes.
Thank you.
So I have a question sort of going forward here. So we'll have contracts soon. And so I guess what role do you see this playing in trying to prevent undefined behavior, or at least bring it up to the developer's attention in terms of actually causing exceptions when they are causing it to fail to compile?
I don't see undefined behavior as an exception, but again, as my efficient compiler and his evil one gets more and more efficient and more evil, more things can be reported as a warning. That is the ultimate idea. How contracts start to change that, they've got to build that into the language. They're going to have to make provisions to make sure that there are more definitions about undefined behavior.
What it would be nice to see, and this is a tooling and implementation issue, is the ability for some of the static analyzers to, for example, suggest contracts you could put on your functions to guard against the inputs that cause undefined behavior. I mean, that would be a really useful tool to say, you know, this function has undefined behavior if you pass an integer larger than 2 to the 19. And it would say, here's the contract you could apply to this function so it can never be called in that context. But since contracts are still a work in progress, it's not clear that the contract specification is going to be rich enough to cover all the cases. Like, I don't think the originally constness of a variable is something you could test in a contract, so that won't be possible.
Thanks.
Thank you. Any other questions we can? Okay, well, again, thank you for coming. We really appreciate it.